Hello, good afternoon. Welcome, James King. Today his topic is distributed programming in Python, a model for strong eventual consistency. Let's give him a round of applause.
Thank you. Thank you. So I just want to start off by thanking PyCon for putting on, or PyCon CA, the organizers, putting on this event and having me here today. So my talk is called Distributed Programming in Python, a model for strong eventual consistency. Unfortunately, I am not from the school of good talk titles, and you'll see why in a bit. So it's just a bit about me. I wrote my first Python program in about 2004. It was just a little program that just calculated the Pythagorean theorem and found the longest side of a triangle. But about 3 years later, I started writing distributed programs with it. So, just a little bit about distributed programming. What comes to mind when I say distributed programming? Does anybody have any ideas? There's lots, right? It's kind of a big field. But nevertheless, the cloud is becoming a lot more prevalent, and I know that's a loaded term as well. But we've got a lot of services that we can build these days that need distributed services like iCloud or web games, so on and so forth. So let's start off with a slight problem in distributed computing. You want to play a game with your friends. A game is unfortunately a little bit Machiavellian. You're all locked in a room, separate from each other. And in order to play together, you can only send messages to one another through tiny little tunnels with messages carried by rats. All right? So at any point in the game, you can only receive messages from your friends, and you can send messages out about the state of your board, which is the state of your program. And you're all trying to get to a consistent state. So you all want to see the same board so that nobody makes an invalid move, things like that. The problem is coordinating this, as you can imagine, is probably very, very hard. As soon as you have multiple actors that can only communicate via channels, they have to imagine what everyone else is doing, what the state of their board looks like, and that can lead to many complications. So far, the main solution for this traditionally has been coordination. So there's a lot of coordination algorithms that try to coordinate the state between all these remote agents or the poor, unfortunate souls locked in these tiny little rooms. Coordination, there's things like Paxos, things like that, that strongly order the way the messages are sent. And so when they're received, you get them in a specific order. And when you apply them in order, everyone gets the same state. The board remains the same. There's also mutual exclusion to think about. So when someone tries to access a critical section of your program, say the board game, they want to make a new role, move their piece on the board, you want to make sure that only one actor at a time is having access to the board. Otherwise, you can get to causality issues where, in your game of trouble, your piece knocked out someone else's piece, but they made a move before you, and then the board's in a different state than it should be in, and then nobody can agree on how it's supposed to go. So we go to great lengths to achieve consistency. We've added tons of algorithms, from the naive of just passing around tokens to Paxos, where we have hard mutual exclusion, we have voting, we have a whole bunch of ways of managing coordination. Screw it. It's too hard. These libraries, unfortunately, you've got like Zookeeper. Somebody did a talk on Zookeeper earlier. Zookeeper uses a lot of the algorithms out of Paxos. So Zookeeper needs to make sure that all the participants in a cluster are at the same state, and they do that using total ordering and all these really complicated algorithms under the hood. As a user, it looks kind of easy, but as a developer, building applications on top of this stuff can get pretty difficult. There's also another problem with coordination, where as soon as you have to coordinate something, you have to think about how it can fail. And when it fails, what are you going to do with it? So you get layers upon layers upon layers of problems, and as each layer you try to fix something, something else gets broken. or can get broken. We live in a very imperfect world. So we want systems that are distributed because we have many, many devices that need to share a calendar together. We have friends we want to play board games with online. But the network is disorderly. Failure happens constantly, and there are other ways other than total ordering, we can get eventual consistency. But that also sounds really complicated too. We need tools to simplify the problem. Fortunately, languages are tools for programmers. We use them all the time to simplify problems. Sometimes we make problems more complicated than they need to be. But we can take languages, or we can take concepts out from distributed programming and we can put them into a language that we can use. Then we can program over the concepts and leave the implementation details to the implementers of those languages. I'm going to talk a little bit today about a language called Bloom, which comes out of Berkeley. There's a research group there called Berkeley Orders of Magnitude, and they've been doing a little bit of research into creating programming languages for the cloud, so to speak. Bloom takes data log and adds the notion of time to it. So who here is familiar with their relational theory, with data log, with anything like that? A couple people? All right. So data log is a sort of a sentential kind of database. You've got relations, which are like in relational theory, they're like your tables. And you add facts to this database of stuff, and you can query it with rules that create a subset of the rules that fill some sort of logical constraint. However, data log is also kind of a static database. It has no notion of time in it. It will never, you cannot retract fact from a data log. It's meant just for querying data. But how do we use it in programs? Well, this is an example of a Bloom program from one of its first implementations, which I know this is a Python talk, but bear with me, is in Ruby, and it's an embedded DSL in Ruby. At the top, we use data log tables. In this case, we call them tables, but we use them to manage our state. So all the information on our board, or in this case, our shortest paths example, we have all of our state as represented as tables. You can see the name of the table, the schema, and all of that. Next, we've got, like in Daylog, we've got logical rules that get applied over time. So a typical program in Bloom is executed in units called ticks, which are just like logical times. It's just a counter, an integer at each tick. It'll evaluate all the rules in the system and derive the next state to apply to all your tables. So just to look at some of the rules, there's always a left-hand side and a right-hand side. In the left-hand side, you've got a table, you've got an operator in the middle, and on the right-hand side, you've got an expression that produces some sort of collection. The operators in this language have a notion of time. In this case, we have that little less than equal sign. That means merge the right-hand side into the left-hand side. You can think of it as merging this tick right away, immediately. There are other operators I'll show later that have different meanings in time. So you've got a deferred merge operator, which means all the information on the right-hand side will get merged into the left on the next tick. You've got retraction, and this is where it differs a little bit from data log, is that you can, because we're dealing with state and state changes over time, we can retract facts from our tables. We also have an async merge operator, which is kind of a special one that allows us to merge the right-hand side into the left at some unknown asynchronous point in time. Collections also have a lot of the normal relational operators we're used to. It has joins, aggregates, projection, which is like basically you can think of like as map. So, why is this cool? Well, we have a language and we have a way of sharing state, but unfortunately, there's still a problem. We still have the potential for coordination in this kind of system. a relational table has no concept of maintaining eventual consistency by itself. And consistency in eventual consistency is kind of, sorry, screwed up here. Consistency in eventual consistency is very difficult to maintain. It's kind of one of the hard points of the total ordering or the Paxos world is that, yes, you have all the complication of all those algorithms on top to maintain the total ordering of the messages, but you're free to think about, or free not to think about consistency issues, basically, is the goal. So eventual consistency removes the complication of coordination, but it introduces a problem where our data may not be safe. It could lead to inconsistent states, which we don't want. We can do something about it. This paper, Logic and Lattices for Distributed Computing, I learned about this paper once I started getting interested in this stuff in the summer from Neil Conway. He gave a talk at Basho on this paper, this very paper. You'll probably see some points that I'll cover that were covered in that talk as well, but let's get to it. Math time. In order for this stuff to work, we have lattices. And lattices basically are a set which has no order, as we know. And well, when we talk about lattices, we're talking about joint semi-lattices. So it has a set. It has a function they call a join in the mathematical literature. And the join creates a partial ordering for the set. So we know that which value is greater than or less than another. It's a binary function. And it also establishes a least upper bound. So the join function has to have these three properties in order for what I'm about to show you to work properly. It has to have associativity, commutative, and it has to be idempotent. So idempotent means it's deterministic. Whenever we merge one value into a lattice, that we always get the expected value out, and it'll never change on subsequent runs. Of course, commutative and associative, same thing. We have to have operators or functions that are commutative, so it doesn't matter the order of operations that you apply them in, things like that. So what we get is, say, two example people trapped in our little room. They have a lattice now to manage some state. In this case, it's a set lattice, so maybe it's all the players in the game. So we start off the same. We start off with an XY and an XY, player A, player B. Player A presses the button, gets a roll, moves his piece around the board. Someone comes, joins the game. We get a Z in there. B gets a different value. They get a V. When they finally converge to send their messages to one another, we call our join function on it, and we end up with the same set at the end. So we agree on the state, and our state is consistent. What's really interesting about the three identities I showed you is that it doesn't matter the order that this happens in. All right? So anytime we want to trade a message, we can trade it. It doesn't matter the order of it. We'll always, all the players, as long as they receive all of the messages at some point in time, they'll get a consistent view of the board or the game. Not terribly interesting still. What we really need in order to make programs with these things are monotonic functions. Monotonic functions allow us to ask interesting questions about the state of a lattice at any given time, which we need in order to write neat programs with them. So we have a set lattice that has three values in it. A monotonic function can map one lattice to another safely and still maintain consistency. So the set lattice, we apply a size function to it. We get a 3. That's just the size of the set. It's called a max lattice, and a max lattice is a different kind of lattice that only ever has increasing integers in it. We can say greater than or equals 5 on the max lattice, and we get a bool lattice back, which tells us it's not greater than 5 at any point in time. Great. So we have shared state. We have a logic-based language for deriving new state at every tick of our program. We have data structures that give us eventual consistency. We don't have any coordination, but we can still do better. It's not enough for me. Neil Conway and his team came up with a way, something called COM analysis, which is basically consistency as logical monotonicity. And all that is a static analysis tool that allows you to guarantee, to analyze a given Bloom program and tell you whether or not that program will eventually be consistent, provided that you have a network that's going to deliver your messages and all the replicas get the messages at any point in time. This is very useful as a language tool, because now we can write a program and we can see where in our program we might need coordination and where it will be consistent and monotonic and all those lovely things. This is an example of what you might find in a sort of a Paxos kind of zookeeper type thing, where you have a bunch of replicas who want to receive votes and they want to know when they've received quorum. So they want to know that they've received enough votes to do some action. We have our state block with all our tables. We have a block of rules that we apply at each tick, but unfortunately, not quite monotonic. Our COM analysis would catch this, because we're using a votes.group, which is a relational group operator to group all our votes down into a single vote table. And we're sending out the result once we have a great enough quorum size. However, once we switch those with lattices, we get monotonicity here. So lattices will only ever increase in value. They'll never retract a fact. So you don't get the retraction operator with lattices, but you do get the ability to be monotonic, which allows you to get all the nice properties of being consistent despite ordering. So I promised you that I would talk about Python at some point. So my project for the past little while has been Knockblock, which is my implementation of Bloom in Python. I was hoping to have the ability to show you a running program in Knockblock today. Unfortunately, we're still in early days with Knockblock. I've got all the lattices that we have in the original implementation in Bud, which is in Ruby. We have an ABC, an abstract base class that lets you define your own lattices. And I've started work on collections, which form the basis of all the tables and things like that. So what we still need, however, in Knockblock is a parser, or a rules rewriter, not necessarily parser. And my plan is to take the same attack that Bud has with using the Python parser to just parse all the syntax as Python, use a rule rewriter to rewrite the rules at runtime, or the ST at runtime, and get back what is called a push-based data flow graph. And then we need an evaluator on top of that. So there's a bit of work to do. The blueprints are in place, and if anybody finds this, I hope I've convinced some of you this is interesting stuff, that you'll join. So that's the GitHub there. You can check it out. So I just want to finish up by saying that it's still in early days. Like, I'm working with InternApp right now on the cloud team, and we're building Openstack, which is an open source cloud platform. It's very neat what we can do already, but it's still kind of like the early days of the NES. I mean, there's good stuff ahead. We just need better tools in order to make better programs out of it. So let's make distributed programming easier by giving programmers better tools for writing distributed programs. Let's remove some of the complication out of writing those programs. Let's take some of the complication out of managing libraries and having to understand mutexes and Paxos and all that stuff. Let's try and write systems where some of those concepts are baked in, so that we can now move on to questions. So anybody have any questions? We've got about a minute left. There's a lot more that's under the hood that we can get into. All right, let's go to some bonus slides. This is a set lattice implementation in Python. Not much there. Really, really works well though. It's all kind of functional, so we're always returning a new lattice. We have little decorators that will tell the evaluator that a given function is monotone or it's a morphism. And a morphism is just a subset of a monotonic function. Basically, the difference is that monotonic functions kind of map a lattice to another lattice where, because you can think of it as the cardinality of the results are kind of the same. So like a map on a set lattice if you're trying to add some numbers together, as long as the result's the same size. But a morphism can change the size, so contains returns a bool lattice, which isn't the same size as a set kind of thing. It's one way of thinking about it. I don't know if this is quite large enough, unfortunately, but trying to squeeze a lot in there. This is the actual meta class and the ABC for defining your own lattices. This one here, we've got the basis of the collections. So there's some places where we can simplify in Python. It's a very nice language for some very basic patterns that you get a lot of built in. And also a lot of good libraries too. We have like SQL Alchemy, we've got Twisted and Tornado and PyPy even, which could enhance performance of these sorts of applications. Oh, okay. If anybody has questions, feel free to tag me and hit me up, and we'll talk distributed programming.